Welcome back to the Explainer. With all the focus on flashy cybersecurity tools, we almost always overlook the one silent, totally invisible protocol that literally keeps the global economy from collapsing. So what is keeping trillions of daily transactions, secure communications, and vast distributed databases perfectly aligned across the world? Well, let's dive into this. Today we're looking at the hidden infrastructure that keeps global business secure, the Internet's invisible metronome.
Here is our roadmap for today. We're going to start with Section 1, the digital symphony orchestra. Then explore the threat of clock drift. Next, we look at Stratums, which is the hierarchy of time, followed by the network delay math. And finally, we'll cover financial security and business risks.
All right, Section 1, the digital symphony orchestra, why the Internet needs a metronome.
To really grasp the high stakes here, we first have to wrap our heads around the massive and frankly chaotic scale of the globally distributed Internet. Think of it like a globally distributed symphony orchestra. You've got cellists in Tokyo, violinists in London, and maybe a percussion section in New York. Now imagine if every single one of those musicians was playing at a slightly different tempo, just reading their sheet music at their own arbitrary pace. What happens? Absolute chaos ensues, right? It would sound awful. Well, the Internet operates exactly like this. It's a sprawling network made up of millions of individual computers, routers, and servers. For this digital orchestra to actually function and process global business data, every single device absolutely must agree on what time it is, down to the exact millisecond. And that brings us to the ultimate conductor fixing this digital chaos, the Network Time Protocol, or NTP. It's a networking protocol operating over UDP port 123, and it ensures global computer clocks are synced up within milliseconds of Coordinated Universal Time, or UTC. You can really just think of NTP as the Internet's invisible metronome. Without it constantly ticking away in the background, our whole global network simply collapses under the weight of its own timing errors.
Moving right along to Section 2, the threat of clock drift, the physical vulnerabilities of hardware.
Now, you might logically think, hey, computers are perfectly digital, they keep perfect time once they're set. Actually, scratch that, they don't, at all. Their clocks are fundamentally based on physical, imperfect quartz crystal oscillators. Let's walk through why they fail to keep perfect time. First off, temperature fluctuations inside the computer case. As a server heats up under a heavy workload, the frequency of that actual piece of quartz changes. Second, there's just the physical aging of the hardware itself, which naturally degrades its accuracy over time. And third, electromagnetic interference from surrounding electronics can subtly disrupt the signal. Because of these gritty physical realities, continuous background synchronization isn't just some nice-to-have IT feature. Correcting this so-called clock drift is an absolute inevitability.
So how severe is this threat, really? Well, take a look at this number, 60 seconds, or potentially even more. Within just a matter of days or weeks, those physical factors we just talked about can cause a computer's internal clock to drift seconds or even entire minutes away from the actual time. And in the digital world, a 60-second discrepancy isn't just a minor inconvenience, it's a massive gaping hole that completely shatters secure connections.
Which leads us to Section 3, Stratums, hierarchy of time and determining the real time.
Okay, so how do we actually solve this globally? We obviously can't have every computer on Earth pinging one single master server. The bottleneck there would crash the system instantly. Instead, NTP avoids this whole mess by using a highly resilient, fault-tolerant hierarchy known as Stratums. At the very top, we have Stratums 0. Now notice this source here. These aren't your standard computers. These are atomic clocks and GPS receivers. They represent the absolute truth of time. Then, we step down a level to Stratum 1, which are the primary servers physically wired directly into those Stratum 0 devices. Next are Stratum 2, secondary servers. These guys query multiple Stratum 1 servers over a network connection and use some pretty clever algorithms to intelligently discard any outliers, maintaining incredibly high precision. And finally, as Stratum 3 and below, we find our everyday consumer devices. So the smartphone in your pocket or the laptop on your desk is pulling its time from servers run by Apple, Google, or the global NTP pool, all cascading perfectly down this trusted chain.
But really quickly, I want to throw in a brief, somewhat terrifying fact about the technical boundaries of this protocol. Warning: reaching Stratum 16 indicates that a device is entirely unsynchronized. That is the hard limit. If your system hits Stratum 16, it basically means it has totally lost its tether to reality and is just flying completely blind in digital space.
Let's look at the mechanics in Section 4, the network delay math, the 4 timestamp exchange.
So let's see how this builds into the actual nuts and bolts of synchronization. We have to address a really obvious question here. If a server tells your computer the exact time, how on earth do we account for the time it takes for that data to physically travel across miles and miles of internet cables? If the data takes 50 milliseconds to reach you, the time it carries is technically already wrong by the time you get it. To demystify this, NTP uses a brilliant little ping-pong exchange of 4 specific timestamps. Let's compare the client's perspective on the left to the server's perspective on the right. T1 records the exact moment the request leaves your computer. T2 is when the server receives it. T3 is when the server sends the reply back. And finally, T4 is when your computer actually receives that reply. By capturing these 4 exact moments, the protocol perfectly tracks the precise journey of the data packet back and forth.
So what do we actually do with those 4 timestamps? By applying this time offset formula, which is T2 minus T1 plus T3 minus T4, all divided by 2, your client computer can calculate exactly how far off its own internal clock is from the server. And here's the absolute kicker. It calculates this while completely ignoring the time lost while the data was physically traveling through the internet cables. It's basically math acting as a flawless bridge between a faulty hardware clock and an atomic standard. Pretty genius, right?
Which brings us to the climax here. Section 5, Financial Security and Business Risks, the High Stakes of Milliseconds.
Listen, this isn't just some abstract IT curiosity. These are incredibly high stakes. Let's outline the real-world business disasters that happen when clocks drift, because it directly contrasts the strict perfection required by digital systems with those messy physical hardware imperfections we discussed earlier. First up, cybersecurity. Secure HTTPS and TLS connections rely on certificates with incredibly strict valid from and valid to dates. If your clock is off, it might falsely reject completely valid certificates, just instantly halting your web traffic. Second, finance. Wall Street stock market trades happen in literally microseconds. If clocks are out of sync, the system physically cannot determine which order happened first, leading to massive collisions and catastrophic financial errors. Third, logging. Say a cyber attack happens. Your administrators rely entirely on system logs to investigate. But if your servers have conflicting timestamps, reconstructing the exact timeline of that hack becomes absolutely impossible. And finally, distributed databases. Global businesses rely on synced databases to maintain data consistency. Without exact timing, older data can accidentally overwrite newer data, silently corrupting the whole system from the inside out.
It is truly amazing to take a step back and realize that our entire global economy relies on this. Taming the chaos of millions of drifting hardware clocks since 1985, originally designed by David L. Mills. NTP is literally one of the oldest protocols in existence, yet it remains undeniably essential, operating quietly in the background to ensure our modern digital world ticks in perfect unison.
Which brings us to our final, absolutely critical thought for today. Are your organization's clocks keeping perfect time, or are you drifting toward disaster? You know, it's a question you should probably go ask your IT infrastructure team today. Thank you so much for joining me for this explainer. Keep learning, keep questioning, and for sure, keep your metronomes synced.